people. So we're going to be explaining standard enthalpies of formation today. So what we covered in the last section with Hess's law with 6.3, the example problem that we had graphite and diamond, we did something called heat of combustion. So you just assume that all your reactants are combusting and you combine the equation, still stuff cancels out. And that's one way of calculating the amount of heat from a specific type of reaction. But another way is by taking a compound and breaking it apart into its elements and seeing the energy of all of those small portions kind of add up to your final product. And that's what this standard enthalpy of formation means. It's the formation of the compound. And in order to solve for these types of problems, we're going to need the appendix. And I will provide you with the appendix as well. But it's an appendix all the way in the back of the book. It shows values. So all of this, it's a table with a bunch of values of all the smaller portions of it. Now, let's talk about this little symbol, the delta HF with the little degree symbol. Whenever you see this little degree symbol, what that is telling you is something called standard states. When you're studying thermodynamics, you'll see this symbol a lot. You'll see that with the delta G. You'll see that with the delta S. And you'll see that with delta H. That what that little degree symbol means is standard conditions. And the reason we use standard conditions is because when we study thermodynamics, you can't really measure something directly. You can only measure the changes that occur. So how did it start? How did it finish? And then you get your delta, your change. How did this property change throughout this procedure? And that's how we get an understanding from things. So in order to make it easy to share data, everyone agrees upon specific conditions to run the experiment so that they know, hey, why does this person has a ridiculous value? Well, they did their experiment in a different condition. You don't run into that problem if you all agree to use the standard states. So here they are. But what I really want to focus on is more of the sample problems, okay? You read this on your own time. You can pause it. This stuff you will pick up more as you kind of just practice with it, all right? The main idea is elements. The energy to produce an element is going to be 0. Your delta H formation of any element is going to be 0. So anything in its atomic state, the delta H is going to be 0. There's a little bit of these rules, okay? So let's kind of check this out. Now, compounds don't have delta H's that equals 0. Uh-oh. Now, this is the main equation we're going to use, but I'll show you how we use it at the bottom, and I'll break it apart, okay? So let's see. Using the standard enthalpies of formation listed in table 6.2, calculate the standard enthalpy change. So that's this. For the overall reaction that occurs when ammonia is burned in air to form nitrogen dioxide and water. So if you want to find the delta H of this process, you need to find the delta H of each of these. And where will you find these? You will find this in your appendix, or you will be given a table with that. All right, now, oh, that was it. Hello, equal sign. So, what does this sigma mean? That sigma is the sum of. So the sum of all the delta H's from your products minus the sum of the delta H's of all your reactants. So products minus reactants. Well, what does the little n mean? The n means moles. The moles of products, the moles of reactants. That's what the P and the R stand for. So let's break this apart and let's start off with the products. We're going to start off with these, or in fact, let's just take a look at our chemical equations that we have for each of them. And right here, I have a few already written out. So the formation of NH3, to make NH3, you need, to make 1 mole of NH3, you need this equation right here. And this is how you're going to find it in your appendix. It's going to show you this equation, and it's going to tell you what the delta H of formation is for that. For NO2, well, half of an N2 plus O2 makes NO2. Same thing with water. Now, why don't we have one for oxygen? Well, oxygen's delta H for any atom or any element in its atomic form is going to be 0. So this is a value of 0, so that's why we don't have it written out. Now the values for the NO2 are over here on this table. Well, that's 34 kilojoules per mole. And then that H2O, that's negative 286 per mole. Negative 286 kilojoules per mole. So we basically have everything kind of ready to put into our formula, but the way I would kind of write it out would be our delta H is equal to, and I will make two giant brackets, one for your products, one for your reactants. And I'll start off with the products. I know the products are NO2, right? But I have 4 of them. So I'm going to put a little 4 because that's the number of moles I have. And then that delta H for NO2 was 34 kilojoules per mole. All right, and what other products did I have? Well, what other products did I have? I had water. So what I'm going to do is I'm going to add, well, there were 6 moles of water, and I know that the delta H for water is negative 286 kilojoules per mole. All right, and then I'm going to move this closer so that way it doesn't feel so far away. Hello, come back. And then let's do the delta H of the reactants. So there, for NH3 was negative 46 kilojoules, negative 46 kJ per mole. However, we had 4 of them, so we're going to put a 4 right here. All right. So there we have it. Now we don't need this information anymore. We have it all we all have it all translated, rewritten down here, right? Maybe I can move it off to the side. Whatever. Let's now do the little bit of math. All right, we're going to do a little bit of math, and we're going to do it by portions so that we don't mess things up. So I know over here on what's in this side of the parentheses, it's 4 times 34. 4 times 34, that's 136 kJ per mole. And then we're going to add, but since there's that negative, I know it's going to be negative. So 6 times 286, that's a negative 1,716 kJ per mole. All right, and we're going to do the same thing over here, 4 times 46. And since this is negative and that's a negative, I know this is going to become a positive, so plus 184 kilojoules per mole. Now that we have everything written, we can kind of add it all up. So our delta H of formation, right, of the reaction, or the delta H of the reaction, sorry, is, let's see, 136 minus 1,716 plus 184. That gives us negative 1,396 kilojoules per mole. And that right there, that's our delta H value. Now, your book does a crazy job of explaining it. And let's see if I can show you. It does a kind of a terrible job. So I would actually suggest not reading this portion. Yeah, this visual doesn't help me. Maybe it might help you, but it does a very, very bad job, I think, of teaching this. So I'll do another example problem like this on the next video. All right. See you then. Hasta luego.